Hello, I'm Maity, and I'm going to talk about theory of singly and doubly reinforced beams. Now, singly reinforced beams, basically what we understand is beams carry bending loads. So there are a few basic assumptions. That is, plane section remains plane after bending. At the maximum compression strain is 0.0035. The ultimate bending failure takes place, and at any point of stress at any point of steel and concrete is equal to the stress corresponding to the strain from the stress strain curve. So basically that is proving that telling the stress strain curve is valid. Now the maximum stress in beam is 0.446 FCK, which is taken as 0.45 FCK for practical purpose. If we see this diagram, it is basically a singly reinforced beam. This is the strain diagram, this is the stress diagram. Now the strain diagram, this is maximum 0.0035 is the compressive strain, 0.87 Fy by Es plus 0.002. This is the strain in steel, which actually should be here. So it should be here. Basically, it should be here at the level of steel. So the strain 1.1 by 1.15 is 0.87, which 1.15 is basically a safety factor, which is valid over a region of 0.8 Fy to the actual stress strain curve. Now for design we can see that sigma y is the curve that is there, and sigma y by 1.5. 1.5 is a safe factor for limit state of design. We always design it at a lower value. Uh, we always design taking a factor of safety in hand. Now in case of the stress diagram, we can see that 0.426 FCK is the maximum stress, compressive stress that happens, and 0.87 Fy, this is again the stress in steel that takes place. Now elastic modulus of steel is 2 into 10 to the power 5, for concrete is 35,000 MPa in both cases. Now the stress strain curve for steel is basically for a cold work steel, and it is obtained by applying a partial shift factor of 1.15, as I said. Now there are three kinds of sections for a singly reinforced beam. There is a balanced section, under reinforced section, and over reinforced section. So what is a balanced section is one where the tension in steel reaches its yield point simultaneously as the concrete reaches its failure strain. So basically the strain and the concrete fails at the same time. Now in case of the yield strain in tension, if in case the yield strain in tension reaches before the concrete reaches its failure, the section is under reinforced. And in case the strain in concrete happens, the concrete fails before the steel yields, it is over reinforced section. So now it is always preferred to design a beam with under reinforced section, because we get some signs that as soon as the steel starts to yield, like there is cracking, there is unrealistic deflection, which gives us signs that the thing is failing, and we can have enough time to repair it or take precautions. Now if we do an over reinforced section, the beam would just collapse as soon as the concrete fails. The beam would collapse, which we need to avoid at any cost. Now where there is something that we know, that steel stretches, there is something happens after the steel. As soon as steel starts to yields, there is something called strain hardening happens in steel. So the strain hardening helps us giving all these signs that the cracking and deflection, and we can take proper precautions for that. This is a diagram for the depth of neutral axis, to how to calculate the depth of neutral axis. Now this is basically sigma CBC is basically this is from the working stress method, but we are using limit state method. So sigma CBC is basically here the 0.6 FCK, 0.45 FCK, and sigma ST by M is 0.87 Fy by Es plus 0.002. Now stress and compression and tension is equal at equilibrium. So if we can calculate that, we can get the value of x, the distance of neutral axis. So calculating P is equals to FST and AST. P tension is FST into AST. Compression 0.6 FCK into x into B. We find this value basically from this diagram, the stress diagram that we can see, if we take that whole thing as a rectangle and the outer parabola is there, so if we have the area of rectangle minus area of the outer parabola, we get the area of that parabola inside. So that parabola, if we calculate, we get this value basically, that 0.36 fck into x into b. Right, equating these two, we get the value of x. Fst is equal to 0.87 fy. So xu by d is this 0.87 fy ast by 0.3 fck into b, which is given in IS 456 and it's g. Now, there's something called limiting value of x by d. Now, limiting value basically depends on the grade of steel in IS 456, and the clause we will see that the limiting value is given for different grade of steel. Now these values are basically obtained. Now say sometimes in special cases the seals are used which is like 450, it's 450, 550 grade, 580 grade, or like 420 grade. These values has to be obtained manually, the limiting value. So x by d equals to strain in concrete by strain in concrete plus strain in steel. Strain in steel is 0.87 fy by es. Now fy, if you change, you get the value of strain in steel. Strain in concrete is constant, 0.03035. Now importance of this limiting value is, in reality the stress strain diagram that we see is not basically like that. It becomes a drooping stress strain curve. Now what happens is compression failure takes place with sudden release of energy. Now as soon as this happens, if the concrete fails before the steel yields, the beam would just collapse without any warning, and we have to avoid that at any cost. So the important few notes that has to be maintained while designing a beam is, you have to provide minimum of 3% tension reinforcement. There should be 2 rebars at the tension zone and not more than 6 rebars in one layer. So if you're providing 2 layer of beam at the tension zone, there is 1 layer, then the spacing bar, then again the second layer, but not more than 6 rebars in one layer. Dia of the hanger bar should not be less than 10 mm. The hanger bar is basically used for using the stirrups. For single reinforced beam, if we have to put the stirrups, we put 2 hanger bars on the top. So that is done. Now the dia of the bar that is to be used depends on the cover and minimum spacing. The cover will get the nominal cover in IS 456 of table 16, and the minimum spacing is given in clause 26.3.1 of IS 456. So you can check these things. Now, singly reinforced beams, the design procedure I'll go through. The L effective, that is the effective length, is basically the clear span plus half the width of the column from both the sides. So it's basically, if the column is of the same size from both sides, symmetric, so you just have the clear span plus total width of one column. Now effective length you get, then you need to find the L by D ratio, which is given in IS 456 clause 23.2.1. You can find the value of depth from there. Now the L by D ratio is already given. There is for cantilever 7, then for simply supported it's 20, and for continuous beam is 26. So what we do is basically we do not take the ultimate value, we just reduce the value to some extent to keep safety. Like if we design with the ultimate value and the section fails somehow, we again have to redesign. So better take a lower value. For example, like if it is a 20, we take something like 12 or 11, something like that, and we design it. So we always keep ourselves at lower safe side. So step 2 is calculate mu and vu. Mu is wl squared by 8, vu is wl by 2. After that, calculate the value of xu by d. Now xu by d, you can get the value from IS 456 and xg. After getting the value, check it with the xu by x by d limiting value given in clause 38.1. The xu by d value should not exceed the limiting value. Now coming to the step 4, the calculating the limiting moment, which is again given in annex G of IS 456. Now how to understand single reinforced beam or double reinforced beam is, if the mu limiting is greater than mu, then it's a single reinforced beam. Now if the mu limiting is less than mu, that is there is some extra moment coming, we need to provide some extra reinforcement on the top, that becomes a double reinforced beam. Calculating AST is given, again there's another quantity equation given, that is in clause G 1.1b. You can calculate the AST required, number of bars you want to provide, and the design is done. Now the whole thing can also be done as per IS 456. Get the value of mu by bd square, get the value of d dash by d, and you can get the value directly from the table, the percentage of steel required. Now using the percentage of steel, we basically calculate the shear strength corresponding to the table 19 in IS 456. So the shear strength that is becomes a tau c. Now calculating tau b is bu by bd, which is again given in IS 456 in clause 40.1. So the tau b and tau c, there is a relation. Like if tau b is less than tau c, you can provide the minimum reinforcement that is again given in clause 26.5.1.6, that is ASV by b into SV. ASV is the area of shear reinforcement, b is the width, SV is the spacing. So we basically get the spacing out. ASV is basically we provide 8 mm rod, so we can calculate the two-legged 8 mm rod. It becomes basically 100 mm square. So that can be done. Now if tau b is greater than tau c, you have to provide stirrups that would actually resist a shear of VUS, which is calculated VU minus tau c into V into B. That much has to be calculated. It has to resist that much of shear. So the spacing can again be calculated from the same clause that is in IS 456, that is given 0.87 F point to ASV into T by SV. ASV again we know, BUS we know, everything else we know to get the value of spacing, and we check the spacing that it should not exceed 0.75 B or 300 mm. Clause is 26.5.1.5. Okay, this is just a drawing for singly reinforced beam. You can see that there is two minimum bars that is provided on top, main reinforcement provided at the bottom. Those middle reinforcement is, since the maximum moment comes in the mid span, we provide 100% reinforcement. We can reduce the reinforcement to 50% near the support. Now that also has to be some length, that is the reduction of reinforcement can only be done at length of 0.08 L from the face of the support on both sides. Now there's also the LD anchorage length. The length LD has to be calculated. Now LD by 3 is the length that has to be from the face of the support inside the support. That much has to be provided. So this is a basic drawing for singly reinforced beam. Okay, double reinforced beam. Why we provide double reinforced beam is like we provide reinforcement at both tension and compression zone. This becomes necessary when the depth of the beam is restricted and the beam has to carry a moment that exceeds the value mu equals to k into f sec into b into d square. Okay, now this value is again calculated from the during singly reinforced beam. We can also get this value in IS 456 where k is a constant and there is this modified value is given in IS 456 in Annex G. In case of a continuous beam, we get a negative moment at the support and positive moment at the midspan. Now doubly reinforced beam are designed in this case. So sometimes the compression member reinforcement helps improve the ductility of the beam. It is also important for shear building like earthquake resisting building. Compression reinforcement has to be provided. Generally, every beam is designed with a compression doubly reinforced. We can not provide much of singly reinforced beams. Now, doubly reinforced beam procedure is exactly same as the singly reinforced beam. You get the value of xu by d and find if it is within the limiting values and all. Then the most important thing comes is finding the mu limiting value for IS 456 and HG. After finding the mu limiting value, we check if it is greater than mu or less than mu. If it is less than mu, you need to provide the compression reinforcement for the extra moment that is coming. Now to find the compression reinforcement, again it's given in the IS 456 in Annex G, clause G 1.2, mu minus mu limiting equals to FSC into AC into D minus D dash. Now D minus D dash, this D value can be, FSC value can be calculated from IS 456. It's a formula is given, but there is something, strain value is needed. Now at the stress level and for the type of steel that is being used, you get the value of strain. So substitute the value of strain, substitute Fs, find the value of ASC. Now mu by m minus mu limiting is known, you get the value of ASC. Now the total steel has to be that AST is equals to AST1 plus AST2. AST1 is the tension reinforcement, AST2 is the compression reinforcement. Now how to find the value of AST2 is again given in the code, AST into FSC by 0.8785. So calculate AST1, AST2, you get the provide reinforcement as needed, get the value of rods. This is a basic drawing for double reinforced beam. You can see that there's some provision, like you can put the, since shear basically takes place near the support, you put the stirrups closer near the support, wider near the span, at the span. Now you cannot put as wide as possible. There is a limiting, it should not be more than 450 mm at the mid span, and in the near the support, the first stirrup should be 50 mm from the face of the support. It should not be more than 50 mm from the face of the support. So these are a few provisions that are there. Okay, coming to the cross section of the beam out here, it is cover is provided, again nominal cover plus the stirrup size and all these things. Now there's the hook that is provided, the stirrup should not be only in one direction from the whole beam. It has to be opposite. Like if it is in the, as shown in the figure, the next stirrup should be in the other side, again the next on the other side, so it should be opposite. Moving on to the flanged beam, there's provisions given in the about flanged beam. In case of a flanged section, the expression for moment resistance and the limiting moment can be found in IS 456 Annex G. In the clause G 2.1, now if XU is less than thickness of the flange, moment can be calculated just like we calculate the moment resisting moment for singly or doubly reinforced beam. Now in case of there's two conditions, that is if df is less than d, is by d is less than 0.2, the moment formula is given in G 2.2. If df is by d is greater than 2, again the moment formula is given G 2.2.1. Now calculating all this, and there's one problem with this, that these expressions are only given for a symmetric flange section. That is, if the flange length is different in two sides, up and top and bottom, then there's a problem. You have to do it manually. Now, for a cantilever beam, the design procedure for a cantilever beam remains exactly the same as a simply supported beam. A few things that needs to be checked in a cantilever beam is the deflection. That's the most important part. Now, clause 23.2.1 in IS 456 gives the maximum value of deflection that can be allowed, but there is some modification factors. Now, as I said, that we always take a lower value of that limiting deflection, and we design the beams at first. Now Fs can be calculated from the expression. There's a figure 4 given in IS 456 where you'll find a graph with a few lines of Fs. Fs is basically can be calculated by 0.58 into F by area of steel required by area of steel provided, area of cross section of steel required and provided. Now after providing these area of steel, we get the value of Fs, so we know which line to refer in the graph. Give me the percentage of steel, tension steel in that is provided, go up, where it hits the line, go left, you get the modification factor. So using the modification factor, we can increase the limiting deflection values to some extent. So that helps us to see if we are in the limits. Sometimes sometimes the value exceeds a bit after the design. So if we see that doing a modification, using the modification factor, if the value is within limit, we do not have to redesign the whole beam again. One more very important thing about cantilever beam is providing the development length. We calculate the development length from IS 456.6.2.1. The formula is given there. It's sigma s 5 into sigma s by 4 tau b 4 so it's given. So that it's, I'm sorry, tau bd, I think it's 4 tau bd. So it's basically LD is given 5 into sigma is by 4 tau bd, or you can also find the value of LD from the code SP16. From the there's a table given for 250 grade of steel, 415 grade of steel, or 500 grade of steel. You can get those values from there. Now anchorage length that has to provide inside the support for cantilever beam is LD by 3, and in case of simply supported beam it is LD by 2 that has to be provided. Uh, so that's it for this time. I'll get back again sometime. Thank you.